Welcome to the Control Engineering webcast, Resolve Robotic Challenges Using Bin Picking Intelligence with ACTINAV Autonomous Bin Picking, sponsored by Universal Robots. I'm your moderator, Mark Hosky, and I'm happy to join you today on behalf of Control Engineering and CFE Media and Technology. Here are some tips to help you get the most from today's webcast. If you're experiencing issues with your slide or audio, refresh your browser or click the Refresh Media button directly under the presenter's picture. You can control the volume of the webcast by adjusting the volume on your computer or by adjusting the volume on the webcast platform. If you're having technical problems with the audio or the slide presentation, click on the question mark at the top right corner of your screen to access a list of system checks to try before contacting an online technician. But if you do need a technician, type a message in the Ask a Question box and someone will get to you as quickly as possible. Individual technical questions will be answered in the Answered Questions box. Type questions for the speaker in the Ask a Question box on the left side of your screen. The live Q&A session will begin after the presentation concludes. Today's webcast is being recorded. You will receive an email within a week with the link to the on-demand event. To download a certificate of completion and a PDF copy of the presentation, use the Event Resources tab on the left side of your screen. Those documents will also be available with the on-demand version of this webcast. I'm happy to introduce today's distinguished speaker, Silas Neal, Channel Development Manager with Universal Robots. After nearly a decade in business operations, Silas entered the automation space and gained 6 years of experience as sales engineer with Cognex and Keyence. Last year, he joined Universal Robots with a strong background in robotics and machine vision. His experience in 2D and 3D vision has carried over into the robotic bin picking arena, and he regularly consults with clients and prospects on this challenging area of automation. He also holds a bachelor's degree from Roger Williams University and is based in the greater Boston area. Thank you for joining us, Silas. And the floor is all yours.
Thanks, Mark, very much for the warm introduction. And certainly a thanks to Control Engineering for having us today. And many thanks to all of you for joining us and taking time out of your afternoon. My name is Silas Neal, and I'm a Channel Development Manager here at Universal Robots. My role is to work with our channel partners, systems integrators, and their end users to ensure a positive experience with Universal Robots. I'll show my contact information at the end of the presentation, and if I can be a resource to any of you, please don't hesitate to reach out. A quick look at the agenda for today. I'm going to provide you with a very quick introduction to Universal Robots and our history in the collaborative robot space. We'll take a brief overview of our UR+ ecosystem and how ACTINAV fits into this ecosystem. I'll review the bin picking landscape of today and the associated historical challenges of this. I'll show you how ACTINAV provides a precision part pick and present for a variety of applications with a primary focus on machine tending. Then we'll look at the technical specifications of ACTINAV and compare it to some other bin picking technologies on the market. Then I'll look at an application fit and some use cases, along with some customer successes that we've had. And then finally, we'll have an open Q&A session to address some of your questions. So a brief introduction to Universal Robots for you. Universal Robots is a company of around 680 employees, and we're in over 40 different countries. UR is headquartered in Odense, Denmark, where all of our robots are manufactured. We've deployed over 42,000 cobots worldwide and hold approximately 50% of the market share for collaborative robots. Our partner network is over 700 strong, which includes both distributions along with systems integrators. Our UR+ store offers over 200 certified UR+ partners, UR+ being our peripheral ecosystem that I'll describe for you a little bit further on today. Looking at our family of cobots shown here, we offer 4 robots with varying payloads and reaches, with the name of the robot denoting the payload. So our UR3E being a 3 kilogram payload robot with a payload of 16 kilograms for our 16E, which is the latest addition to the family. While we're on this page, I'd like to briefly note that the ACTINAV bin picking solution currently supports the 5E and 10E robots, with plans on the roadmap for the 16 kilogram robot. The actual ARM specifications themselves, all of our E-Series robots deploy with a built-in force torque sensor. We have 17 layers of safety functionality certified by TUV. We offer easily replaceable joints and a touchscreen pendant where all of your programming is done, including the ACTINAV bin picking solution. The E-Series, again, our latest generation of cobot, has a number of improvements, including an improved programming flow, which we'll dive into a little bit further in the presentation, along with some wizards for payload estimation, center of gravity, and palletizing routines. There are also a number of safety features built into the new E-Series, including protective stop prevention and force, speed, boundary restrictions in the elbow. A cobot can be thought of as a tool similar to a wrench, hammer, or a screwdriver. Using collaborative robots is significantly easier than the typical deployment of most types of traditional automation. Collaborative robots can quickly and easily be deployed to automate all or just a very small part of a process. This unique functionality allows for human workers to work with the cobot side by side and add value to each other's strengths. Typical applications that cobots excel at are your standard pick and place, packaging and palletizing, machine tending, assembly and screw driving, quality inspection, but also path-dependent operations such as gluing and dispensing. However, we're not limited to just these types of applications. Sometimes apps can be very specific, such as cleaning parts with CO2, for example. These are applications that we see automated every day with tremendous success. They're common across all types of manufacturing and are proven to be great fits for cobots. There are, however, unique applications that could be a pain point for your facility. I really like the application that's shown here in this photo. The production team is using the robot to get the best angle while working in very close proximity to the robot. They're able to comfortably focus on their work as if the robot wasn't even there. All right, moving along to our UR+ ecosystem and how this links in with ACTINAV. UR+, this is how UR+ is broken down. The UR+ is our overall ecosystem. UR+ components are just that. They're going to be your peripherals that work seamlessly with our software and our robot. And then UR+ application kits. These are kits that combine those UR+ components with a software targeted at solving a very specific application. ACTINAV falls into the UR+ application kit. So just to clarify the UR+ piece here, the components are certified by UR and are those individual components such as cameras, end effector, and other accessories. They're general purpose and can be integrated by end users, distributors, integrators, or machine builders. The UR+ application kits, again, take those components with a layer of very custom software that makes solving a specific application easy. These are going to be focused on categories such as sanding, welding, palletizing, and of course, bin picking. So ACTINAV is a UR plus bin picking kit. It takes a 3D sensor from PhotoNeo with a variety of available UR plus end effectors, and it has a really easy to use software through our UR cap. So this leads us to the landscape associated with bin picking and machine tending. Bin picking has been around for decades at this point, and I certainly don't want to pigeonhole ACTINAV into just machine tending. However, it's an area where we found it to be a really great fit and easy to justify. So just to clarify and keep minds open, ACTINAV is suited for anywhere that you need a part placed in a very repeatable and accurate manner. So there are a great variety of bin picking applications out there, but we are largely targeting machine tending of metals, plastics, and components, and I'll explain momentarily. But here you see we've got some large automotive and heavy equipment work cells, some e-commerce, and that's simply not a good fit for us, and we are, again, targeting the machine tending. When looking at these heavy equipment work cells that you most often see in automotive, they're typically very fast with very high throughput, and they require safety features including guarding and scanners. They also require weeks of programming time and certainly a tremendous amount of resources and specialists. Entry into these systems are often into the multiple hundreds of thousands to millions of dollars. And to be able to justify that cost, the parts are going to be very long run in that 3 to 8 year range. And systems like this are going to be a bigger challenge to redeploy should the project change. Contrasting that, logistics such as your e-commerce and order fulfillment oftentimes involve integrating with ERP systems, calling databases, and they're going to be a really large IT project. These are more commonly pick and drop applications, or stab and grab, if you will, placing parts into boxes or other totes. In many situations, the product is going to be in a flexible packaging, which requires flexible grippers or long and cumbersome end effectors. Certainly has a place where appropriate, but not a good fit for ACTINAV. And these e-commerce based are going to be more surface identification with vision rather than a CAD matching of the part. We've determined that ACTINAV is suitable for machine tending of the metals, plastics, and the components. In a lot of circumstances, it's a single part going from a bin into a machine, which fits really well with ACTINAV. Most machine tending applications require a very precise pick and placement of the part as well. The simple teaching method of ACTINAV allows for really smooth retrofits into existing stations that are already in production, and it's fully collaborative. I'm going to very quickly address the 3 Ds that are associated with machine tending. It's dirty, dangerous, and dull. As many of you know, machine tending is a repetitive job, and it can oftentimes be dangerous. The ACTINAV system is designed to offset these challenges as well as address a variety of labor issues, including absenteeism, high turnover, high labor shortages, just labor issues in general. Automating the process of machine tending, however, is a lot more than just programming a robot. It means integrating conveyor systems, bowl feeders, custom tooling and fixturing. In a lot of circumstances, parts are already in the bin, which makes going direct from a bin into a machine a flexible and scalable option. But of course, bin picking can still be a challenge. So we are introducing ACTINAV, a bin picking system that's simple and reliable. The ACTINAV autonomous bin picking takes a market-leading collaborative robot with Universal Robots, a PhotoNeo 3D sensor, an autonomous robot motion control to solve unstructured bin picking and accurate placement for machine tending. So the big takeaway here is unstructured bin picking to a very accurate placement of the part. So next, I'd like to play a couple of quick videos for you just to let you see this in action. Next, we'll take a look at the autonomous motion module and look at a couple of videos. ACTINAV actively navigates the robot autonomously into the bin, picks a part, and then moves through the environment collision-free, then placing the part accurately into the machine. You'll notice as these videos continue that no two paths are the same. The AMM takes into consideration the trained environment that we've given it, as well as the bin and other criteria, and then also works to make sure it avoids any type of singularities and other obstacles. In this particular video, it's picking heavy cast parts from the drive shaft family, as you can see. The robot moves to the home position here, out of the sensor view for image acquisition. And keep in mind, it's always planning multiple paths ahead. So it picks a part and moves it to a conveyor belt in the top of the video. This particular video represents a customer application where they had an hourly operator standing by an angled bin, picking parts, and then feeding them to a conveyor system, which then took the parts further downstream for continued processing. So here it's placed the part on the conveyor belt. We'll pick a part and you'll see it's a completely different path this particular time. In this second video, the robot is moving through space in a collision-free way. The product that it is picking out of the bin are plastic, either gas or oil caps, using an internal gripper. It places the part in the fixture where an operator can move it towards the next process, in this case being an O-ring inspection. But the robot could also be taking these parts and placing them into a regrip station for repeatable placement into a machine, depending on how the part was picked. All right, so speaking to the autonomous operation of ACTINAV, the system is designed for both tended and autonomous machine tending. From a justification standpoint, ACTINAV addresses a number of key needs, most oftentimes associated with machine tending. The Autonomous Motion Module, or AMM, plans the path collision-free. So no more workstation repairs, and it's fully collaborative. The ability to scan deeper bins allows for less refilling and more parts per bin, leaving you with less human labor requirements for the bins themselves. And accurate placement of the parts have always been a big challenge. We'll discuss some of the repeatability a little bit more in depth further down the presentation. Speaking to the ease of use with ACTINAV, universal robots are known for ease of use. Here at UR, we use the verbiage teaching our robot rather than programming. All of the code found in traditional robots is completed in our UI using basic commands like move and waypoint. The same ease of use applies with ACTINAV. All of the programming for your bin picking project is done on the UR Teach pendant, and we utilize the same teach by demonstration for setup that we do with your typical standalone collaborative robot application. Another advantage with ACTINAV is that it's going to be quick to deploy into your factory. There are 6 simple predefined tasks in the UR cap on the Teach pendant, which walk you through the entire setup process. You can expect between 6 and 12 lines of programming for a bin picking application versus hundreds without the autonomous motion module. I mentioned earlier that all the setup was done on the Teach pendant. This is a snapshot of what the URCap ACTINAV user interface looks like on the UR Teach pendant screen. The bin and the surrounding environment are taught by demonstration, touching the actual objects and adding them to the virtual environment. So to do so, we first ensure that the system is ready. Secondly, we'll configure the 3D sensor and align it. The system deploys with an alignment marker, which we show to the sensor in a series of various poses. Third step would be to configure your tool and define any clearance shapes. Then we'll define the environment surrounding the system, so any obstacles that could be in the path, a pedestal, a pillar, perhaps the fixture that this ACTINAV system is sitting on, we would want to program. And then we'll define the bin. So bins have always been a big challenge for robot entry and exit. We'll show at the sides, the tops, and the bottom to actually train and define that bin. Finally, we'll load a 3D CAD model of the part and scan to teach. It's important to train the environment, of course, so that we can avoid collisions. Since no two paths are the same with ACTINAV, we need to add clearance shapes. In this particular example here, we are training a capsule shape, which represents the 3D sensor in the environment. For the environment training, we can use spheres, capsules, or lozenge shapes. So first, we will train the points for each end, shown here, point 1 and point 2. Then we could change the name of the actual shape to its appropriate name in the program, such as 3D sensor. Then we'll input the diameter here of the capsule shape representing the sensor. And then finally, we'll input the length of the sensor. And as you can see here, we've now trained that capsule shape, which represents the 3D sensor, so that we can avoid any type of collision. That being said, I think a video will do better justice than I will, so I'm going to play a quick video here for training the environment for you. Here, the operator is going to train the environment, starting with the sensor. He'll do all of the training, teaching, on the Universal Robots touchscreen pendant. Now he'll use free drive to freely move the robot around through space. Free drive allows you to apply a force by hand in order to position the robot where you want it. Next, he'll show the system both sides of the sensor, as shown here, to avoid any types of collisions. Now the operator will move to train the bins, where he'll show the system the sides, the bottom, as well as the top of the bin. So here he's training multiple points on the sides of the bin. And we'll move to the top of the bin, and then continue on to program the bottoms of the bin. When it comes to the teaching of the part, the ACTINAV system uses a scan to teach. Step 1 is to import a CAD model of the part into the teach pendant using a USB. We'll then attach the part to your end effector of choice. We'll position the part under the scanner in the field of view and press scan on the teach pendant. And from there, you just have to simply position the part at the locations for place, pre-place, and post-place using free drive. So keep in mind, this is not remembering a robot pose, but rather the position of the part in space. The robot joints are autonomous and are going to be in a unique combination each time. So in terms of ease of use and the simple teach by demonstration, the ACTINAV system is exactly that. So next I'll show you a quick video about how to train the pick and the place. In this next video, the operator is going to use the scan to teach functionality to show the robot both the pick and the place locations. To actually train the pick, the operator just simply attaches the part to the end effector, hits scan, and acquires an image. The system will remember both the part location and the orientation. Here, he uses free drive to move the robot and the part to the place location. Once both the pick and the place locations are trained, ACTINAV can continue operation.
Hey, great. Thanks for that video, Silas. We're going to go on to a poll question right now and ask our audience, so what machine tending applications could a universal robot with ACTINAV help you with? And the choices of the poll are CNC, milling, grinding, polishing, plastics, drilling, tapping, welding, inspection stations, test stations, or other. And you can check all that apply, and we'll review the results at the end of the presentation. So take a look at the poll there and check off what applications that you think this robot might help, and we'll review the results near the end. Thank you. Silas, back to you.
Thank you, Mark. So on top of solving labor shortages, we found the return on the investment to be under 16 months for this product based on a two-shift operation. Here in New England, the average setup time from unboxing both the robot and the bin picking system to deployment is less than 2 days. So a drastic reduction in deployment time compared to other bin picking technologies. With the depth of the bins that we can support, you can expect a longer runtime between bin filling, and certainly a higher reliability on the system as the two main components, the UR robot and the autonomous motion module, are made to work with one another. So let's take a look at some of the most common machine tending applications, and this relates to the survey that we are taking now. When looking at CNC, milling, grinding, polishing, the ACTINAV system can support quite a number of different workflows. Your first being your typical picking from a bin and placing into a machine where orientation isn't as critical, a bin to a regrip fixture where the robot will place the part in the fixture, release, and then pick the part back up again so it's in a repeatable position prior to placing in a machine. A bin to a multi-slot fixture, perhaps waiting for the next process, and this is where the value of UR palletizing wizard certainly matches up with ACTINAV. A bin to a rescan to a fixture, or to maybe an inspection camera prior to placement in the machine, and of course a bin to a conveyor, which then continues the part further along the process. So next, we'll take a look at how ACTINAV actually works and some of the key functionality behind it. Some of the key features here, the first being the automatic path planning piece. This utilizes the 3D sensor and the environment information that we provided and trained to automatically generate a path at runtime. Traditionally, this would require waypoint programming with no environment information to help avoid collisions. Whoever was programming constructed individual waypoints to cut the problem up into smaller sections. Trying to take into consideration the environment has always been an obstacle. The adaptive path planning piece, ACTINAV generates an optimized path every time. There are no programs, waypoints, or poses. It's a complete end-to-end path from the pick all the way to the place. Alternate technology requires construction of the path using a sequence of waypoints and fixed moves, which isn't always practical. The programmer also has to use an end effector that's equal in height to the bin depth in order to avoid collisions and keep that robot above the bin. With the free spin pick and the part relative place, I'll show you an example on the next slide, but we use a single trained pick, which automatically generates hundreds of possible picks. The single trained part relative place results in thousands of possibilities for robot poses to achieve the place. Combine that free spin pick and the part relative place, and we enable thousands of pick and place path options that give us a really high pick success. Historically, you need one trained pick paired with one robot place pose. Doesn't really provide accurate orientation with the placement of the part. And finally, all of the programming or teaching is done on the UR teach pendant. One environment for the entire process. So this eliminates the need for two completely separate programming environments. The UR script that's being created by ACTINAV is completely locked down. You can, however, continue programming prior to and after that path planning. So for those of you familiar with UR, you can program in the UR world, enter ACTINAV, and then re-enter the UR world, as long as you're in the same pose as you were when you left the ACTINAV. So free spin pick is a function of the proprietary nature of this system, and it allows the tool to spin a full 360 degrees for the approach and the exit without collision. So here it's going to allow tool rotation around its Z-axis at a given pick point. This slide does a really, I think, a good job of highlighting why ACTINAV. It's a breakdown of how simple the programming really is. Free spin pick combined with the autonomous path planning and the part relative place allow just one pick per side, so 2 lines of programming. A 6-sided part ordinarily has 3 pickable points and thus 6 lines of code with our system. More traditional bin picking requires 8 to 12 picks per side at 10 lines per pick, leaves you with over 240 lines of code. Next, I'm going to play a short video for you here that gives you a good breakdown of the adaptive path planning. This next short video clip illustrates the adaptive path planning of ACTINAV. The part shown here has 3 different sides that it can be picked from. Each path is unique based on the pick location on the part. So in this next pick and place with the blue color, you'll notice it's a completely different path, but it's also placing on the other side of the fixture. So it's doing the pick and place collision free, but it's also avoiding any type of joint singularities. Some bin picking, the more vision-based bin picking, you don't have that visibility to the joint limitations. But again, here, no path is going to be alike. And this final illustration with the comparison of the colors does a really good job of illustrating that. All right, next we'll dive into some of the features and benefits of ACTINAV. The automatic path planning drastically reduces the programming time and the skill set requirements of the programmer, as well as the overall project complexity. This reduces deployment time by weeks. If your environment changes, we simply model the change and the rest of the program adjusts. This leads to a drastic reduction in overall project risk. With the adaptive path planning, it gives you an overall reduction in the integration complexity and no manual determination of paths. Stoppages that are due to collisions are eliminated, and it provides you with simply a more reliable system. With the free spin pick, this enables more part types and applications which typically require precise and accurate orientation placement. This allows you to address multiple times more the number of applications with ACTINAV. And again, all programming on the universal robots teach pendant. It's all integrated into the program tree. This means for you less learning requirements and less training for a successful deployment. When considering ACTINAV as a bin picking solution, there are a few key attributes to take into consideration. First being a single type of part in a bin, and this is most critical. So it does not support mixed parts in a bin. We do support a variety of different end effectors, whether it's suction, magnetic, internal grippers. The sensor does need to be fixtured directly above the bin. It will support different angles of bins with some small and obvious limitations there based on an angled bin. A rescan or a regrip will certainly increase the accuracy of the part placement if your cycle time allows for it, but the direct bin to place accuracy is in that range of plus or minus 3 to 8 millimeters, depending on the resolution of sensor that we use. Our ideal application has a cycle time of that really 10 to 90 second range. We found it difficult to justify anything above a 90-second cycle time, but that 10 to 90 second range. In terms of the part shape, symmetric, axisymmetrical, or non-symmetrical parts, there's just a minimum thickness requirement of either 2 millimeters or 5 millimeters, and that's just simply for the contrast for the 3D rendering. So a quick look at some other technologies and how it compares to ACTINAV. ACTINAV utilizes a single sensor, which relies on CAD-based matching algorithms. Thinking back to some old bin picking systems that I've seen in the past with 4 cameras, the calibration is a nightmare if an operator knocks into just one of the sensors. Other bin picking technologies often rely on lower resolution 3D sensors that use AI or training of a pickable surface. While this can sometimes be faster to set up, it's going to be a far less precise means of doing it. ACTINAV is designed for a single part type in the bin. Other bin picking products do sortation and they do part identification with a large variety of parts in a bin. We found that with machine tending, this doesn't apply. And that's more focused on the e-commerce sector. High accuracy placement into chucks and fixtures is possible without the need for a regrip using the adaptive path planning and part relative place. A majority of other bin picking products focus on pick and drop applications which don't require a part to be oriented at the place. These are going to be your basic pick and place applications only, and they rely very heavily on secondary fixtures. The automatic path planning combined with the trained environment means that the robot can utilize smaller end effectors and maneuver and operate inside of constrained machines. Without this path planning, other solutions require long end effectors, which don't work well in constrained machines. Furthermore, path planning means that the system can work in deeper bins, which means less bin tending and longer runtime between bin refills. Others are requiring shallower bins, which simply require more tending. And finally, our cycle time we're really targeting is the 10 to 20 second range. Industrial and those high-speed applications in the sub 10 second range are just really not a good fit for this system. So next, I'd like to take a look at some of the part qualification and some applications where ACTINAV has been a good fit. So here we have some examples of your typical parts that are best suited for bin picking and most often seen, whether it's metal, plastic, fiberglass, cast parts, stamped parts. The general rule of thumb for ACTINAV and part selection is going to be 2 fists or less. Parts larger than that are going to fill the bin with too few parts, which makes it a lot more challenging to justify, and it could also lead to payload limitations with your really heavy cast parts. So continuing on, cast or machine parts that have multiple picking surfaces. Anything cylindrical has some good options when it comes to picking. Gears and rings with an internal grip end effector have done really well, especially here in New England. And then flat parts, and again, as long as they have that minimum thickness of 2 millimeters to accommodate the sensor. So I'd like to show you a quick video here of an application that we tested in our lab, just to show you some of the different projects that we can solve. So this next video example shows an application that we tested for a customer in our lab. You can see here we're using a magnetic end effector for this project. Where applicable, we can certainly recommend end effectors that will demagnetize the parts so that you don't have any residual magnetism. And again, this just shows the robot in the home position when the image is being acquired and taking a new path every time for accurate placement into the fixture. So commercially speaking, many of you are likely wondering what's in the box. So the ACTINAV system is made up of an autonomous motion module, which is that little black box that you see below the teach pendant on the right image. A 3D sensor, which is from PhotoNeo, is available in 2 different sizes. The general rule of thumb for bin sizes is going to be either 0.5 meter cubed or 1 meter cubed, and I will send out this presentation at the end for anybody that's looking for those true tech specs. It comes with a UR cap, an alignment marker for the 3D sensor, cables, screws, brackets for mounting, and all of the appropriate manuals. And the kit also includes either a UR5E or a UR10E currently. From there, the distributor would add a frame, an end effector that matches the application, any intermediate fixtures or inspection cameras, and any of those peripherals. Next, I'd like to show you just a very quick video of our training facility to show you what the training looks like for ACTINAV. This is just a really quick video clip for you to speak to the training that we have available for this product line. This is our training facility located in North Reading, Mass, where trainees can get hands-on with the ACTINAV system. All of our North American UR offices are equipped with ACTINAV demo units, and we are offering virtual product demonstrations through both our partners as well as our UR offices.
Hey, great. So now we're going to take a look at the poll results. Everybody participated, I hope, and we're going to go ahead and take a look at those results, push them out to the audience. So we have inspection stations in the lead. with about 35% of respondents. Next looks like other applications. So I know, Silas, when you've talked about universal robots, people talk about being how amazed at various applications that the robots apply to. So maybe you'll have some other applications to explore here. And then other drilling and tapping, about 10%, 11%, CNC, 8%, plastics, 8%, welding, 8%. So a nice diversity of possible applications.
Yes,
Any
I would
comments, Silas?
say so.
Yeah.
No, this is great, and I think excellent feedback for us on our side. Yeah, Mark, to your point, the universal robots can accommodate a large array of different applications, and so this is good feedback for us as well. Yeah, thank you. So I guess to kind of summarize here, ACTINAV is an autonomous bin picking system that accounts for the vision aspect of bin picking, which is finding and locating the orientation of the parts. But not only that, it also accounts for the full end-to-end motion, which includes part relative placement. So it's a complete end-to-end path from the pick to the place. And looking here at whether that's grinding, plastics, inspection stations, there's quite a wide array of answers here. It looks like it could be a great fit for all of those. It has that same ease of use that comes standard with our standalone collaborative robots and a quick deployment. So thanks to everybody for joining. I'll leave my contact information up here for just a moment. If I can be a resource to any of you, make some local introductions geographically to my counterparts. If you have any feedback on the presentation today, perhaps things that are left to be desired, I certainly welcome all of that feedback. I'll hand it back over to Mark.
Great. Thanks, Silas, for the presentation, the videos, and the advice. And now we have time for audience questions. The audience may type in questions for the presenter in the Ask a Questions box on the screen, and we'll get to as many questions as time allows. Questions that we do not get to today will be posted online at controleng.com with the archived version of this webcast. Remember to download a certificate of completion or a copy of the presentation by using the Event Resources tab on the left side of your screen. And now on to the Q&A. So let's see. We have here what is the maximum weight which can be handled by the pick-and-place robot? I know you mentioned a few models involved.
Yes, so currently the two supported robots are going to be the UR5, which is our 5-kilogram payload robot, and the UR10E. So a 10 kilogram would be the maximum payload that we can support right now. There's certainly plans in the future to support higher payload with the 16E on the roadmap. Good question.
Great. Does the pick-and-place robot work in a dusty environment?
Yes, so it most certainly would. So the robot itself and the teach pendant are going to be IP54 rated, and the control box for the robot are going to be is IP44 rated. Excuse me. So IP44 and IP54 rated.
So that would encompass a lot of different applications.
Absolutely, yes.
Another question, what about replacing humans in repetitive piecework operations like welding, stripping, twisting, packaging, testing, those kinds of things where there might be injuries involved?
Absolutely, and that definitely comes back to that dirty, dangerous, and dull, right? So if an application falls within the bin picking sector and can be done with ACTINAV, that's a great solution. But with applications like welding, twisting, we have a lot of talented systems integrators and distributors alike that have solved tremendous amount of applications like this. So we have a welding partner in Colorado, for example, that does a full turnkey system for us. So yeah, any of those repetitive and dangerous operations, we can certainly support that. Yep.
So here's several questions related to the bin picking itself. How difficult it is to train parts for the bin picking when the geometries are different as the parts are sitting in the bin. How can you easily program for all possible variations? And then a related question about mixed parts in a bin. Can it deal with mixed parts?
Right, great question. So I'll start with the portion about mixed parts in the bin. So ACTINAV is best suited and really only support one type of a part in a bin. When you get into having even different geometries within a bin, that's where it gets tricky. So it is designed for like a high run where you have one single part, same geometry in a bin, and it's just loading that over and over again into, say, a CNC or a mill, for example. The system itself, however, can support up to 100 different parts. Each of those parts just has its own program. So let's just say 100 different bins of parts, assuming that it was all one single part within that bin. So we can certainly store quite a number of parts, but it's not for mixed bins.
Great. So let's see. Audience can continue to submit questions that they may have. Again, we'll get to as many as we can. Next question. Can you comment on the vision software configuration and the vision system and integration with robots? Many people who may have done robot system integration before, it can be quite a challenge when integrating with vision systems, as you well know from your background.
Absolutely. So if you're thinking about a more vision-based system, like a Picket, for example, it's really strictly a vision-based solution, right? So it provides you with the X, Y, Z coordinates of the part, and the user needs to program all of the different waypoints in and out of the bin. So with the ACTINAV system, it accounts for all of that. So it's providing you with a complete solution that does all of the path planning for you. So I guess if the question is, what kind of visibility do you have to the vision software and the configuration, it's all done for you internally and locked down. However, we can certainly support vision inspection afterwards. The robots handshake really well with other vision systems. So if you want to pick a part from a bin and present it to maybe a barcode reader or a 2D vision system for some kind of inspection, after looking at the survey earlier, it would appear like quite a few folks on here have inspection applications, so we can certainly support that.
Great. How are the motion paths determined? Does only the picker end watch for collisions, or are all the elbows protected against collision? So let's see, to be precise, where are the sensors placed?
Yes, good question. So the sensor itself, the 3D sensor, is placed above the bin, and that's where we'll take the image, get the image, and actually send that feedback to the robot. But as far as the motion paths and how that's determined, we've trained it all of the environment, right? So we've trained it the 3D sensor, we've trained ACTINAV, the fixture that it's sitting on, any obstacles that may be in its path, we have to train. So that's the most important piece, is that obviously we need to train that environment for it to avoid collision. So when it acquires an image, the robot is in its home position, grabs the image, and then it's starting to plan multiple paths ahead. It automatically eliminates anything that would cause a collision, and then the next step would be to make sure that it avoids any type of joint limitations, any singularities, things like that. So, it has to take into consideration the inverse kinematics for that actual path planning.
Another question, how are the European offices doing? Is there an office in Romania, for example?
We do. We do have offices in Romania. This product, the ACTINAV product, is not yet available in Europe. So it's only available in North America currently, with plans on the roadmap to deploy to Europe in the near future.
So a question about ROI and some skepticism. How do you figure ROI on a project like that? And then some related questions. How does it work on highly reflective surfaces or parts in a bin? And then on cycle time, how are we doing on cycle time?
So on the cycle time piece, we are targeting, again, that kind of a 10 to 90 second. We found that from a justification standpoint, your 10 to 20 second range is really going to be the sweet spot for that. We have a large network here in the U.S. I have counterparts all over North America, and we can certainly work with customers to put together a plan for the return on the investment, right? Talk about current throughput, talk about how many shifts you're running, parts, things like that, and can absolutely come up with a plan. And then it looked like the final piece, Mark, you said was shiny parts, reflective parts, things like that.
Yep.
Yeah, with the wavelength sitting at 638 on that sensor, we've had pretty good luck with some shiny parts. I mean, certainly transparent parts can be a bit of a challenge, but we've had quite a bit of success with that red laser. So there's only one way for us to truly know, and that is for us to test it out for you. That's our job.
Related to that, you mentioned there are two sizes of vision systems that can go with it. Does performance vary, or how do you choose between them?
Yes, so great question. There is a 3D sensor that has a scanning range, a depth of field, if you will, of that 458 to just a little over 1,100 millimeters, and then a larger field of view, and of course scanning range that sits in 870 to just over 2,000 millimeters. And so with that, we're going to support different size bins. I don't have specifications as to the true loss of resolution as you go to the larger field of view, but that's certainly something that we could come up with in partnership with PhotoNeo.
Great, thanks. And maybe one more question. How does the system work with an application that experiences vibration?
An application that experiences vibration. So I'm curious if that means the overall production facility just has lots of vibration, or if it's the bin vibrating, things like that. You know, I think the big obstacle, as you can imagine there, would be with the image acquisition piece. So that's something I'd like a little bit more details on as far as the vibration and the source of that, but certainly something we could overcome.
Great, thanks so much. Silas, great presentation. If anybody else has questions that they would like to submit, we can get to those offline. We're going to wrap up for now. We appreciate the videos and advice. And for the audience, for all the great questions. We will try to get to as many of the unanswered questions offline as we can. Thanks again to our presenter, Silas Neal, for sharing his time and expertise. Also, I'd like to extend many thanks to Universal Robots for sponsoring today's event. Now that we're just about done, we want to hear how we did. The exit survey will pop up on your screen as soon as the webcast ends. Please take a moment to complete it because we use the information to improve our webcast. On behalf of Control Engineering and Universal Robots, I'd like to thank you for attending. This concludes our webcast. Thank you and goodbye.